In a previous video, we saw how concentration can affect rate, and we developed that relationship and used it in the form of what's called the differential rate law. It says rate is equal to a constant number times the concentration of a reactant raised to some order, some power. Today we're going to focus on the relationship between time and concentration, starting with the differential rate law and then using the methods of integral calculus to come up with this other relationship called the integral rate law. Now, if you don't know calculus, if you haven't had it yet, don't worry about that. You don't need it to really understand the consequences of it, but we are going to go through the step-by-step procedure that we use to show why the integral rate law makes sense, and that will require calculus. If you don't know about calculus, if you're not familiar with it, just wait for the results at the end and you'll be okay. For a single reactant, and we're going to stick with A, the concentration of A is just A in square brackets. That means moles per liter concentration, or some concentration unit. And the rate law, which basically says that rate is equal to K times concentration of A raised to some power we're going to call M. We're working with single reactant here. Could be written this way. The change in concentration of A with respect to time, that's rate, is equal to K times A raised to the M. And this should be a negative number here because concentration of A will be decreasing since it's a reactant. So this is going to be our starting point. And then we're going to use the methods of integral calculus to figure out what is the relationship between time and concentration. And we're going to do this for three different orders: zeroth order, first order, and second order, so you can get an idea of how concentration changes with time in all those three cases. So let's get into a different workspace, and then we'll begin developing these integral rate laws. Starting out with the differential rate law, which says for a reactant, minus change in concentration of that reactant over change in time is equal to the rate, and that rate is equal to a constant number times concentration of A raised to some power M. We're going to develop an integral rate law for M equals 0, M equals 1, and M equals 2. So let's start out with the first case where M equals 0. Now we're going to use calculus notation here. If you're familiar with calculus, you know that the deltas get skinnier and skinnier and skinnier until they aren't deltas anymore, but they're D's. So for calculus notation, we would rewrite this dA over dt is equal to K times A to the, in this case, 0. But A to the 0 is 1, and so this could be rewritten this way: minus d concentration A dt is equal to K. And from this point, we want to develop something we can integrate so we can get a relationship between concentration and time. I'm going to multiply both sides by dt, and this is what I get: minus dA equals K dt. And in fact, I'm going to multiply both sides by negative 1. So I now have dA equals minus K dt. At this point, I'm going to perform a definite integral. I want to go from where time is 0 to where time is any random time that I'm just going to call t. So I'm going to rewrite this dA equals minus K dt. And then I'll set up my integral. On the time side, I'm integrating from 0 to time t. And on the A side, I'm integrating from concentration at time 0 to concentration at time t. I'm going to probably say naught instead of 0, so be aware of that. Let's work on the left-hand side first of all. Now, most of you are used to using x's probably in calculus, so think about this. If you have the integral of dx, what is it? The indefinite integral, or the antiderivative of dx, is just x. So if you're taking the antiderivative of dA, it's just going to be A. So on the left-hand side, we've got concentration of A evaluated from A naught to A at time t. The right-hand side could be rewritten this way. I could pull out the negative 1 and the K, because those are constants, and then integrate dt from 0 to t. And once again, integral of dx is x, so the integral of dt is just t. And so if I integrate this, what I've got is just t times negative k minus k times t, evaluated from 0 up to time t. So now let's evaluate these things. On the left-hand side, I would have a at time t minus a at time 0 equals minus k at time t minus k times 0. So that just works out to minus kt. So now I have a relationship here that involves time, a constant, and two concentrations. One of them is a starting concentration that I know, and the other one is a concentration at any time t. Watch what happens when I rearrange this. If I add a naught to both sides, I get this relationship. Concentration of A at time t equals minus kt plus concentration of A at time naught. This looks like the equation of a line, where concentration of A at any time is y, k, or negative k, is the slope, t is x, and the y-intercept is the initial concentration. That's a form of a line. So think about this graph. If I have a plot of time versus concentration of A, I will have a y-intercept at the initial concentration of A, and I'll have a line on here that has a slope of minus k, and that line can predict for me at any time t what is my concentration at that time. So two useful things we find. First of all, this is the relationship that can allow us to predict concentration at any time if we know the initial concentration and the rate constant. And then this graphical relationship allows us to determine if a reaction is zeroth order if we have nothing other than just time and concentration values. If we plot concentration versus time and we turn out to get a straight line, then that means it's a zeroth order reaction. Let's do this again. Minus dA dt is equal to k times concentration of A, and now we're going to go with m equals 1. So this is a first order reaction. Let's find out what the integral rate law is. We're going to do a similar operation as we did before. First of all, I'm going to make this dA over dt equals minus k times concentration of A. I want to get the t terms on one side and the non-t terms on the other side here. So I'm going to divide both sides by concentration of A and multiply both by dt. So dA over A is equal to minus k dt. Now, reverting back to what we usually see in calculus, this would be like dx over x. And the antiderivative of dx over x, of course, is natural log of x. So when we take the antiderivative of dA over A, we should get natural log of concentration of A. So here's where we're going from here. We're going to take the definite integral once again from A at time naught up to A at any time t of dA over A. And this is going to be equal to minus k times 0 to t definite integral of dt. And we've already done this integration on the right-hand side already, so we know what this is going to be. This is going to be minus kt. On the left-hand side, we're going to have the natural log of concentration of A evaluated from A naught up to A at time t. So that works out to natural log of A at time t minus natural log of A at time naught equals minus kt. And you can imagine what we're going to do next is try and turn this into the equation of a line, which isn't hard to do. Natural log of A at time t is equal to minus kt plus the natural log of A at time naught. So here's our graphical relationship. If I'm plotting time against natural log of concentration, I will have a y-intercept at the natural log of concentration at time naught, and I'll have a line that has a slope of negative k that relates my natural log of concentration at any time to that time. So, two important pieces of information that we have here. One of them is this ties together concentration and time, and the other one is if we make a plot of time versus natural log of concentration, and that turns out to be a straight line relationship, well, then we know we have a first order reaction. One more order to go. Let's try m equals 2. So starting out again with minus dA dt equals, now we have k times concentration of A squared, because we're looking at a second order reaction where m is 2. So dA dt is minus k times concentration of A squared. So dA over A squared is equal to minus k dt. Back to normal math notation that you're used to, dx over x squared, which you could write x to the minus 2 dx. If you take the integral of that, you're going to get negative x to the minus 1. So let's create our definite integral. We're going from a naught again up to a at time t of dA over A squared, and that's going to be equal to minus k times the integral from 0 to time t of dt. So this should be, on the left-hand side, negative concentration of A to the minus 1, evaluated from A naught up to A at time t. And that is again going to be equal to minus k times t. So, evaluating the definite integral. Now I have negative 1 over A at time t minus negative 1 over A at time naught equals minus kt. I'm going to multiply everything through by minus 1/2 to get rid of the negatives. So that tells me that I've got 1 over A at time t minus 1 over A at time naught equals positive kt. So 1 over A at time t is equal to kt plus 1 over A at time naught. So here's the relationship that will allow us to calculate what is the concentration at any given time. And here's the helpful graphical thing. If I plot 1 over concentration of A against time, and I happen to get a straight line relationship, this time it'll be sloping up, positive k, and it'll have a y-intercept of the inverse of initial concentration. That's going to be my y-intercept. Straight line relationship between inverse of concentration and time means that I've got a second order reaction. So that's my other useful piece of information. This graphical relationship allows me to determine if I have a second order relationship. So let's review. If we have a 0th order reaction, then concentration of A, which is a reactant at any time, is equal to minus k times that time plus the initial concentration. So that's the integral rate law for a 0th order reaction. For a first order reaction, the natural log of concentration at any time t is equal to minus the rate constant times time plus the natural log of initial concentration. That's the integral rate law for a first order reaction. For a second order reaction, the inverse of A at any time is equal to kt plus 1 over the initial concentration. That's the integral rate law for a second order reaction. So here are the implications. And let's just review this again. If I plot the concentration of A against time, and I have a downward sloping straight line relationship, that tells me that I have a 0th order reaction. So if m is 0, a plot of concentration of A versus time should be linear. Also, if I have a plot of natural log of concentration of A versus time. And that turns out to be linear. Then I know that I have a first order reaction. A plot of natural log of A versus time should be linear. And for second order reactions, a plot of inverse concentration of A versus time should give a straight line relationship, and this will have a positive slope. Now we're going to do something different from what we normally do. We're going to have a Quizkin in the middle instead of at the beginning. So here's a problem. You have data for a reaction between A and B, and you're supposed to determine the rate law. So now we're talking about the differential rate law, what we learned about in the last video. Stop the video, give this a try. I'll give an answer and then a solution in a moment. Well, this might have given you some initial difficulty because I laid this table out with a different orientation than what you've seen before. And I did that to see if you could really understand what the data was telling you and how to use it, or if you had just memorized the procedure. Here I have the trials in columns, whereas the rate and concentration data was in columns in previous examples. And I have the rate and concentration data as row headings, and that's where the trials used to be before. Well, I'm not going to use the formal math way of solving this, but I am going to just look at it in general terms. Between trial 1 and trial 2, here's what I see. The concentration of A, initial concentration of A, doesn't change at all. However, the concentration of B initially does change. It doubles, goes up 2 times. What happens to the rate? Well, the rate goes from 0.08 to 0.16, which is also a doubling. So if the concentration of B doubles, and that causes the rate to double, here's the relationship between B and rate. It's first order. So far we could say rate equals K times concentration of B raised to the 1 power. What's the concentration of A do to our rate? Well, in trials 2 and 3, there's no change in concentration of B, but the concentration of A quadruples, goes up by 4 times. What happens to the rate during those 2 trials? Well, between trial 2 and trial 3, it goes up not by 4 times, but by 2 times. What does that mean? Well, the rate dependency looks like this. Rate is proportional to concentration of A raised to some power n. If my rate goes up 2 times, and that's proportional to 4 raised to some power n, well, n's clearly got to be 1/2 because I'm taking the square root of 4 to get 2. So I can complete my rate law. Concentration of A is raised to the 1/2 power. We haven't seen that before, but it can happen. Here's another Quizkin. It says for a certain first order reaction, so we know that M equals 1 for this reaction, K is 0.052 per hour. What's the rate when reactant concentration is 0.10 molar? Stop the video, think about rate law, and see if you can come up with an answer. Well, this is a first order reaction, so the differential rate law is rate equals K times concentration of A to the 1. So K is 0.052 per hour, and my concentration of A says here is 0.10 molar, and I'm raising that to the 1 power, so molar is moles per liter. My units are going to be moles per liter per hour, and when I multiply these two together I get 0.0052. You'll have to use the integral rate law to solve this problem. It says for a certain first order reaction, K is 0.052 per hour. That's the same reaction we had in the last Quizkin. Calculate the time required for the concentration to drop to 80% of its original value. Well, this is a first order reaction, so that means the relationship between concentration and time looks this way. Concentration of A at time t is equal to minus kT plus the natural log of concentration of A at time naught. Time is what I'm looking for here, so I'm going to solve this for time. The first thing I want to do is get the natural log of A terms both on one side. So I'm going to subtract natural log of A naught from both sides, and that gives me natural log of A at time t minus natural log of A at time naught is equal to minus kT. Now I'm going to divide both sides by k to get a relationship for time. Time is going to be natural log of a at time t minus natural log of a at time naught divided by negative k. But I could write this a different way. I could write natural log of a at time t over a at time naught over minus k is equal to time. Here's why that's handy. Because I don't know what I'm starting with, but I do know that I want to drop to 80% of whatever it was. So I can pick any two numbers I want because now I've got this in the form of a ratio. So the concentration of A initially, let's call that 1. The concentration at time t then, or when it's 80% of its original value, well, that would just be 0.8. And then K is 0.052 per hour. So the time required here would be the natural log of 0.8, which is just negative 0.22, divided by 0.052 per hour. The units when I divide here are going to be hours, and it's 4.3 hours that it'll take for 80% of it to remain. Well, that last question was a good setup for our next topic, which is half-life. Half-life is defined as the amount of time that it takes for half of a given reactant to be converted into product. That's half-life. You may have dealt with half-lives for first-order reactions in a math class in the past. We're going to look at first-order and zeroth-order and third-order reactions. So for a zeroth-order reaction, we know the relationship between concentration and time is given by this equation here. That's the linear relationship for a zeroth order reaction, integral rate law. Let's determine what half-life would be, starting from there. So if concentration of A at any time is equal to minus kT plus the initial concentration, we want to know what happens when the concentration is 1/2 of the initial concentration. So let's solve for T, because time is half-life. So subtracting A naught from both sides, I get A at time t minus A at time naught is minus K times T. So time is concentration of A at time t minus concentration of A at time naught divided by negative K. So the half-life time would be concentration of A naught over 2, because that means half of the initial concentration is still there, minus concentration of A naught over negative K. Or I could say minus initial concentration of A divided by 2 over negative K is half-life, because this is like 1/2 minus 1. So I'll cancel out the negatives here that are on top and bottom, and I come up with this. Concentration of A over 2K is equal to the half-life. So for a zeroth order reaction, when M is 0, the half-life is the concentration at the beginning of that half-life divided by 2 times K. So half-life depends on the concentration at the beginning of that half-life. That's not true for first order reactions, as you're going to see in a minute. For a first order reaction, natural log of A at time t is equal to minus kT plus natural log of A at time naught. Once again, I'm solving for t, so I'll subtract the natural log of concentration of A at time naught from both sides to isolate the t terms, and then t would be natural log of A at time t minus natural log of A at time naught divided by negative K. Because we're looking for a ratio here, it might be more useful to write this way. Natural log of concentration at time t over concentration at time naught over minus K is what our time is. So at time t, I'm going to have half of the initial concentration. So that means natural log of initial concentration, A naught, over 2, divided by initial concentration, over minus K, at half-life. But if we cancel out the A naught, top and bottom, here's what I get. Natural log of 1/2 over negative K is half-life. If I change this to a positive K by multiplying the bottom by -1, and then multiply the top by -1, I'm just taking the reciprocal inside the natural log. So natural log of 2 over K is equal to the half-life. So this is when first-order reactions are considered the half-life. So it doesn't depend on the initial concentration at the beginning of the half-life. Every half-life is going to be the same for a first-order reaction. You may have seen that before in some form in a math class. Now let's look at second order. For a second-order reaction, 1 over A at time t is equal to positive KT plus 1 over the initial concentration. So I'm solving for t again, so I'll take 1 over A at time t and I'll subtract 1 over A at time naught. If I do that on the right-hand side as well, then I just end up with KT. So time is equal to 1 over concentration at time t minus 1 over the initial concentration divided by K. So the half-life time is equal to 1 over the concentration at time naught over 2, because half of the initial concentration is the concentration at time t here, minus 1 over concentration of A naught divided by K. But this could be written 2 over initial concentration minus 1 over initial concentration divided by K. So my half-life is equal to 1 over A naught over K. Or I could rewrite this more simply, 1 over K times A naught. So this is the relationship that tells us what half-life is when I have a second-order reaction. And again, it depends on what the concentration was at the beginning of the half-life. Notice here that it's inversely dependent on the initial concentration. So the higher your initial concentration is, the shorter your half-life is. For a zeroth order reaction, it was directly dependent on the concentration at the beginning of the half-life, the initial concentration. So the bigger your concentration, the longer the half-life was. And for first-order reactions, it doesn't matter at all what the initial concentration was at the beginning of the half-life. So now you know about the concentration of any reactant as a function of time. And this opens up a whole realm of problem-solving possibilities that I'll give you an opportunity to practice in class.